Alright, for 2 letter C, we have the following series. N equals 2 to infinity, x to the 2n over n ln n squared. And again, we're trying to find the interval of convergence. So typically with our other ones, we want to do the same thing here and use the ratio test. So start with our original equation. So we have x to the 2 n plus 1. Remember that n plus 1 has to be in parentheses when you plug it in for n. Over n plus 1 ln of n plus 1 squared times the reciprocal of our original, x to the 2n, n ln n squared, and we're doing the limit as n goes to infinity. So the only thing that cancels is we have x to the 2n plus 2 and x to the 2n. That leaves you an x squared. Keep in mind you don't need absolute value bars because x squared is always positive anyway. Let's group our other things kind of in a sensible manner. We have n over n plus 1, and we have ln n squared over ln n plus 1 squared. Limit as n goes to infinity of this fraction right here is 1 because these are same degree. We just use their coefficients. We can kind of use the same property here. This is equivalent to ln of n over ln of n plus 1 all squared, since both the top and bottom are squared. And ln of n and ln of n plus 1 grow at the exact same speed. This is essentially like same degree type of thing. That's going to be 1 as well, and then since it's squared, 1 squared is still just 1. So this disappears as well. This was all the ratio test, so this has to be less than 1. So what we get is that x squared has to be less than 1. If x squared is less than 1, that means x has to be in between -1 and 1. So our interval of convergence is from -1 to 1. But remember, now we have to check what happens at -1 and at 1. What you might notice here is that since our original series was written so that x has a power of 2n, that tells us that the power of x is always even. If it's always even, that tells us that -1 and 1 have the same effect here. So we only have to test one thing, actually. Because if we plug in -1 or if we plug in 1, this is still always going to be positive 1, no matter what. So for x equals plus or minus 1, our series becomes just 1 over n ln n squared. So we just need to see what does that mean for the convergence. Does that series converge or diverge? If it converges, both of these are included. If it diverges, both of those are excluded. So that series right there can be done in a couple of different ways. By far the easiest, though, would be the integral test. So the reason you know this is the integral test is that ln n and 1 over n are in the problem together. That is like the makings of a substitution, if you remember, for integrals. So we know that if we integrate from 2 to infinity the function 1 over x ln x squared dx, and we get a positive finite number, then this series converges. So in order to evaluate this integral, we're going to have to do a substitution. Let's set u equal to ln x. That tells us that du is equal to 1 over x dx. So when we plug in our substitution, 1 over x dx is already in the function, so that just becomes du. ln x becomes u. So what we get is 1 over u squared du. In other words, u to the -2 power. That's a very simple antiderivative. We get -1 over u from 2 to infinity, but before we plug in our bounds, you have to switch u back to our original variable x. So we have negative 1 over ln x from 2 to infinity. So let's see what happens when we plug these in. Keep in mind, technically you should be doing 2 to t, limit as t goes to infinity. So we're just going to inherently know that when we do the infinity, we're doing the limit as x goes to infinity. So when we do the first bound infinity, the limit as x goes to infinity for ln x is infinity. So we have negative 1 over infinity, in other words 0, minus whatever we get when we plug in 2. Well, when we plug in 2, we just get negative 1 over ln 2. You don't need to know what that is, but you just get 1 over ln 2. 1 over ln 2 is just some number. ln 2 is a 0.6-ish. So this is just a positive finite number. That's exactly what we were looking for. That tells us that this series must converge because the integral test gave us a positive finite number. So therefore that series converges, meaning at our boundary conditions, negative 1 and 1, we have convergence for both. So our interval of convergence then for this problem is from negative 1 to 1, including both negative 1 and 1.